So, in the last day, I started the module 5, that is network theorem, and there I discussed what are the means basic laws like Ohm's law, KCL, KVL, etc. So, by these basic laws, how a circuit can be um, analyzed, that I have shown you in the last class. So at the very beginning I discussed what is KCL, KVL and some element equations, um, and I also discussed that what are the basic parameters like voltage and current that we need to find out from any circuit, and once we got these basic two parameters like voltage and current, then we can easily find out other parameters like power, energy, etc. So that is why by circuit analysis we try to find out either this voltage or current, basically. And then I have also shown you that what are the element equations. Element equations are nothing but uh, the the equations which represent the characteristics of a particular element. Okay, so for that I have given you some relation between voltage and current waveform for different basic elements like resistor, inductor and capacitor, and by that I have shown you that these equations are the element equations. Like for the resistance, V equal to IR is the characteristic equation or element equation. For inductor, V equal to L di dt is the characteristic equation, and for the capacitor the equation is I equal to C dv dt. So these are the characteristic equation or element equation which represents the characteristics of the basic elements, that is resistor, inductor and capacitor. So after that after that um, I discussed that by using that element equations and KVL, KCL, how the circuit is being analyzed, and for that I told you that means I have shown you that for a very simple circuit, whatever I have considered over here, for a very simple circuit, the number of equations needed, that is very large, that is 10 number of equations needed, because there are 10 number of variables. Okay, so as the number of variables are more, so there will be more number of equations that should be computed to get the value of the variables. Okay, so this is the there also I have shown that how we will use, means how we used that KCL, KVL and element equation to get all the 10 equations which are needed for getting the solution of all the variables, like 10 variables. So that I discussed in the last class, and at the end of the class I think I have ended up with the concept of node voltage. So here again I am starting with the concept of node voltage and branch voltage, and then I will move to the simplified method of node voltage analysis, means more simplified method that we discussed in the last class. Okay, so for realizing the concept of node voltage, here I have taken a very simple circuit. Here I have taken a very simple circuit. Um, so let us go through the last day concept, that is while we are applying KVL. Okay, at the time we mentioned some voltage variable. Okay, so whenever we have a circuit and we are trying to solve the circuit or analyzing the circuit, we just try to put all the current directions arbitrarily. So let us take the direction of current arbitrarily. So this is the direction of current, say I1, I1, and this is your IR3, IR2. So through all the elements I am just putting the direction of current. This is your I1, this one is I2, and this one is I3. Okay, now once I have put the direction of current, so I can now give the polarity of the elements for which the polarity is not mentioned. You can see these are the independent voltage sources. For all these independent voltage sources, the polarity that are mentioned already, but for these resistances the polarity is not mentioned. So as I have put the direction of current arbitrarily over here, so accordingly I will give the polarity. So here the polarity of the voltages will be, voltage across the different elements will be, this will be plus minus, because for the resistors the current flows from positive to negative. So this one is your VR1, and here the current flows in this direction, so this will be plus minus VR3, and the current is flowing from this to this, so it will be plus minus VR2. Okay, and rest the for all the independent voltage sources, the voltage and their polarity are mentioned for V1, V2 and V3. So now you see that in the last day, while I was applying for the KVL, so while I was applying the KVL, while applying KVL, to the independent loops, we consider the voltages which is nothing but your V1, V2, V3 and VR1, VR2, VR3. So these are the voltages that we considered for applying KVL at different loops. So these voltages are called as, all these voltages are called as, so what are these voltages? Can anyone say? What are these voltages? V, R1, R2, R3? Anyone? Hello?
Branch voltage.
Yes, so all these are the branch voltages. Okay, so now the thing is, now I am just going to mention that there are some other representation of voltages that we can do, and by that kind of representation we will later on we will see that the analysis will be much more simpler, where the analysis means where the number of variables will be less. Okay, so so now say, let us say that there are how many independent nodes are there? So 1, 2, 3, 4 and these are the 5 nodes. 5 nodes are there. Okay, and let us say that this node is as I am considering as reference node. So all the non-reference nodes are, let us say this is A, B, C and this one as D. So these A, B, C, D are all the non-reference nodes. So so what we call is that at this A, B, C, D, if we mark the voltage, so voltage at the non-reference node with respect to non-referent nodes with respect to the reference nodes are called as node voltages. So let us put the name of the voltage variable. So let us say this is VA at this node, it is VA. At this node B the voltage is say VB, at this node C the voltage is say VC, and at this node D the voltage is say VD is the voltage. Okay, so therefore for this particular circuit the node voltages are VA, VB, VC and VD. And what we can say that these node voltages may or may not be the voltage across the element, or I can write that this is a important issue, that is the node voltages may or may not be the branch voltages. So in this circuit we can show you the example, like here if I consider the voltage at node A, that is VA. VA is the node voltage at node A, and also the VA is the branch voltage for this V1 independent source, because you can see that node voltage means voltage at the node with respect to the voltage at the node with respect to the reference node. So then if I see that what is the node voltage V, means node voltage as at node A, that is VA. Now VA is the voltage with respect to the reference. So now if I consider this element, now for this element the voltage at the voltage at this terminal of this element is VA, and voltage at this terminal, the other terminal, the voltage is 0. So ultimately we can say that the voltage across the element, that is VA minus 0 is, that is V0, sorry, VA minus 0, that is VA, is equal to V1. Okay, so this node voltage at node voltage VA at node A is also the branch voltage of this V1. Okay, but you see that if I consider this node voltage, that is node voltage at B, that is VB, this VB is not the branch voltage of a particular element. Okay, because here you see that VB is not appearing across any particular element. Okay, but VA is appearing across a particular element, so we can say that VA is also a branch voltage of this this particular branch, but VB is not the branch voltage of any particular branch. Okay, so VB over here is specifically a node voltage, but VA over here is a node voltage, and along with it is also a branch voltage. Okay, so have you understood all what I am just trying to mention, the very narrow difference between node voltage and the branch voltage? That is over here, if I mention, is that VA, for example, VA is node voltage at node A. Also VA is the branch voltage or element voltage or element voltage of the independent voltage source V1. Okay, uh, so this is one thing, and the second one is that VB is only the node voltage at node B. Okay, so is there any confusion? Is there any confusion? If you have no confusion, then I will move to the node voltage analysis. So once the concept is clear, then means I will go for the nodal analysis or node voltage analysis. There are various names that are mentioned at different books. Or we can say node voltage analysis. So for node voltage analysis, what I am just taking, I am taking a very simple circuit. Okay, so this is the very simple circuit that has been mentioned over here, and for this circuit I will apply that nodal analysis. And already you have gone through the nodal analysis earlier, but here at the very beginning what I am just trying to show you that means how by the node voltage analysis we are just trying to reduce the number of variables, and by that number of variables means lesser number of variables are needed to get the branch voltage or branch current for the whole circuit. Okay, so for that particular circuit First, what I am doing over here is just I am putting the name of the nodes. So so first I am just taking randomly I am taking a non means reference node. So let us say this is a reference node, and the non-reference nodes are, say this is node A, this is node B. Okay, and also arbitrarily I am just putting the currents of different branches where no current direction is mentioned. So I have put the current directions over here, and according to the current direction I can put the voltage, means branch voltage value, means what branch voltage value variables over here with their polarity. So the polarity over here for this resistance R2 will be plus minus VR2, and this current direction is downward, so it will be like plus minus VR1, and over here the voltage is downward again, so it will be like plus minus VR3. Okay, so you can see over here I have put all the current and voltages. Okay, let me write the current over here. This is your uh, small I1, this is your small I2, so I3. Okay, so I have put the current and voltage